Okay, good morning. We are meeting again. In the previous class, when I met you, we were discussing about magnetic circuits, and I told you about the equivalent electrical circuit also. So whenever you are doing problems on parallel magnetic circuit, it's always better to check for the equivalent electrical circuit. I just will just let you know why it is important or why I am insisting on that. Before I go to the next section, let me just tell you why I am insisting upon the electrical equivalent also. See, let me take the presentation. So in the previous class, what I discussed with you, actually Deba Miss also said something about parallel magnetic circuit, but still I just wanted to mention something. That is, we had a circuit like this. You were given a magnetic circuit like this, okay, where there were 3 limbs. Okay, let there be a coil here and then 2 fluxes. There you have a flux phi, you have flux phi 1, you have flux phi 2. And I drew an electrical equivalent like this, where I had a series resistance which is equivalent to my S here. Then I'll have 2 parallel paths with 2 resistors, R1 and R2, which is equivalent to S1 and S2. And then I will be connecting a total voltmeter here, or a source equivalent to my Ni. Okay. So what I said was, I have a flux here equivalent to the current I. Then I have I1 and I2, which will be equal to I1 plus I2 will be equal to I, or similarly I have flux phi 1 and flux phi 2. Now, and we attempted to do this, like we said that since the voltage here is the same, or this voltage here across 2 parallel resistors are the same, the total V will be, this is V2, this is V1, this is V, let this be total. We said V total will be V plus this V plus V1 or V plus V2. Anyone can be taken. That is why we calculated like that. And this V total, instead of V total, you wrote this Ni. Ni is equal to, instead of capital this V, MMF there will be phi S. This is also MMF. This is also MMF. Plus phi 1S, which is the MMF corresponding to this. Or this is also MMF. This is also Ni is MMF. Phi S is MMF. HL is also MMF. Phi S plus phi 2S also same. Now, I expected one question from you which you didn't ask. Now, if I have a resistor here and 2 resistors in parallel, I know the total resistance is R plus R1 R2 by R1 plus R2. Isn't it? So, I expected a question from at least one person whether you can take this in a magnetic circuit as S plus S1 S2 by S1 plus S2, where S indicates reluctance. Now you can use this method also. This is correct. So that finally what you can do is Ni, the total MMF, is equal to phi into this total S total can also be done. When you do using this method, the answer will be the same as the answer that you get from this method. This is what I wanted to tell you. The only difference will be, the only difficulty or only thing that you may have to manage is, because you are working with reluctances here, these reluctances, as you know, will have a number of digits in it, 2,35,042, etc., etc., because the reluctance of the air or reluctance of all those iron path, etc., comes. You may have to be very careful about handling those large digits of number of digits. But finally, only the first 3 or 4 digits matter when it comes to I, because it will be divided by that n, 1000 or 10,000 will be coming in the new denominator, and finally you'll end up with the same. So if you are really interested, you can try this alternate method and check whether you are getting the same answer. Am I clear? Huh? I wanted to convey this to you. Did I convey it correctly? Anuja?
Ma'am.
Anuja, did you understand, Anuja?
Yes, ma'am.
Or should I explain this once again? I don't have any problem.
No, ma'am. It's clear.
It's clear. Okay. So that is one thing that I want to tell you. One more thing is, there is a textbook authored by Theraja, Theraja, which was not supposed to be a standard reference book during our days of engineering classes. But nowadays, many students and many faculty find it easy to, the book has gone through so many editions that it has now become one of the so-called standard textbooks of reference or reference books. The PDF is available in the, one or two of you have commented that textbooks are not readily available to you. This PDF is available in the net, and I have just taken one type of question, that is another way of putting the same question to you. This is one question that I want you all to write down. Question number, example 627. Can you just write down this question, please? An iron ring, I'll read also so that it will be easy for you. An iron ring of mean length 30 centimeters. An iron ring of mean length 30 centimeters is made up of 3 pieces of cast iron. 3 pieces of cast iron. Each piece has the same length, but their respective diameters are 4, 3 and 2.5 centimeters. An air gap of length 0.5 mm. An air gap of length 0.5 mm is cut in the 2.5 centimeter piece. In the 2.5 centimeter piece. If a coil of 1,000 turns, is wound on the ring, find the value of current. Required to be passed through it to produce, in order to produce a flux density of flux density of 0.5 Tesla in the air gap. In the air gap. BH curve data of cast iron is as follows. BH curve data of cast iron is as follows. There is a tabular column shown. B and H is given. Now B values are 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Values of B. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Okay. Corresponding H will be 280, 680, 990, 1400, 2000, 2800. Neglect, leakage and fringing effects. Neglect, leakage and fringing effects. Hope you have written down the question. Now, what is the question? We are not going to do the question, but I want to give you just an idea of what it is. Now, the question is that you are given an iron ring. Okay, which is iron ring which is having a total mean length of 30 centimeters or 30 into 10 raised to minus 2 meters. It is made up of 3 pieces of cast iron, which means each piece will have a length of 10. So, and also they have given that there are 3 dimensions. One is having 3 centimeter dimension or 3 centimeter diameter. Another one is 4 centimeters, and then this is 4 centimeter diameter. Then you have a third one which is 2.5. Okay. And within the 2.5, they have said an air gap is cut. This is 3 centimeter, 4 centimeter, and this is 2.5. Now this air gap length is 0.5 mm. The way in which I have drawn is not it is not to scale, nothing, but I hope that gives you an idea. So the flux density here they have given as Bg is 0.5 Tesla. You are asked to find out if at all there is a coil wound somewhere. It's a series composite magnetic circuit. You're asked to find out I. What is the value of I if there are 1000 turns? Now, as before, what you're going to find out is S total. It can be found out in many ways. This is the, I think, is the best manner. S total is S, say 4 centimeter plus S 3 centimeter plus S 2.5 centimeter plus SG, the air gap. SG. This is S4, so S3, this is S4, S2.5, and so on. SG. That is, you will have to find out L4 by mu 0 mu r into A4 plus L3, length of the L3 by mu 0 mu r into A3 plus L 2.5 by mu 0 mu r into A 2.5 plus Lg by mu 0 into what is area here? Air gap area. You have been asked to neglect the fringing. What is that area? This area is the same as that of whatever is there in 2.5. So you can write here, this is A 2.5. Hope that is clear. That is why they have said that the saw cut or the cut has been made for air gap in the 2.5 this thing. And one or two points to note here. Okay. One, what is L 2.5? What is L at all? What the total mean length was L4 equal to L3 equal to total mean length was said to be 30. 30 by, it was divided into 3, 2.5, 3, 4. 30 by 3 or 10 centimeters. L4 and L3. What about L 2.5? L 2.5 would have been equal to 30 centimeters had there been no cut. Because there is a cut, L 2.5 will be 10 centimeters minus 0.5 millimeter. That should be done. Okay. So this value you know, this value now you know, this value you know, Lg also you know. Now coming to A4 you know, A3 you know, A 2.5 you know, here again it is A 2.5. This also you know. Now the only unknown values are now mu r is not given. So mu 0, mu r is not. Instead of that, what they have, what is given to you? They have given you the BH curve. Directly the value for 0.5 Tesla is there. So you can find out B and H is given. Mu 0, mu r, total mu 0, mu r can be found out. What is the relation between B and H? B is equal to mu 0 mu r into H. For a value of 0.5 Tesla, which is given in the question, what is this? You can find what is that as the flux phi g. Flux phi g, or what, because you have Bg. But what you have to understand is the flux remains the same throughout. It is a matter of flux density. Whatever flux is, that is the most important point that is to be noted. Whatever flux is there here will be the same as the flux here, will be the same as the flux here, will be the same as the flux here, because it is a series magnetic circuit. But the flux density varies because the areas are not the same. So I am giving you this as a homework. Can you just do this and come? Let me see what is the answer. We'll check where you cannot be sure that the answer is the same, but then you can check whether this is the answer. Okay. Let's see. All of you should do it by yourself. They have done in another manner. They have written the MMF as H into L and then equated. You can do in whichever way you are asked to do, but then this is one coil current. They have got it as 0.582, this value. Did you see? This value, 0.582 amperes. That is what they are getting. Just check whether you are getting the same or not. Okay. Okay, that's it. So flux density flux can be found. See, these points also you should remember. The common flux for this circuit, flux density, because flux density in the air gap is given, you can find out flux there. Okay. But the flux remains the same throughout because it is a series magnetic circuit. See, I have not done this problem myself. I will also attempt in the manner which I had mentioned to you. And let's see what is the value that you are getting. I will also check. Okay. So that is it. We are stopping the magnetic circuit part. So do you want me to upload this textbook also
Yes, ma'am.
in your classroom? Okay, I'll do that. Okay. I'll do that. Okay, then coming back to our syllabus. So till now, what we were discussing in module 2 was regarding magnetic circuit, the basic terminologies, MMF, field strength, flux density, reluctance, comparison between electric and magnetic circuits that we did, similarities and differences we checked. Then we also discussed about these basic terminologies like MMF. Whenever you think about MMF, think in terms of Ni is equal to HL is equal to phi S. All those are MMF. Ampere turns. Then field strength that we discussed. Flux density we discussed. Reluctance we discussed. Comparison. Then series and parallel magnetic circuits with composite materials. That also we discussed. Numerical problems. I hope this many number of numerical problems are sufficient. If you have got the concept of each of the problems, then it is not a problem to do any such problem. Now we come to more interesting things like electromagnetic induction, Faraday's laws, problems, and so on, Lenz's law. So today we'll just peep into what is electromagnetic induction. I am 100% sure you all know about electromagnetic induction. There may be nothing new that I'll be talking, but yet again, when it comes from another teacher, maybe 1 or 2 points, maybe a new points. Okay, so my favorite area is electromagnetic induction. Electromagnetic induction.